Okay, so we are in Introduction to Statistical Learning, Chapter 6, and we're in the conceptual questions, question 3. Okay, so suppose we're going to estimate regression coefficients in a linear regression model by minimizing this guy. Okay, so if you're not familiar with what this guy is, so this is the residual sum of squares. So we're going to if we were just doing straight least squares, we would minimize this, right? We would minimize the residual sum of squares. So we're finding beta naught and beta j's that minimize that quantity. Okay, and then we're also adding this additional constraint right here, where the sum of the absolute values of the beta j's is less than some value s. Okay, and so when we add this penalty to our least squares fitting algorithm, now we are performing the lasso. Okay, and so that, if you're not, you might be more familiar with it in this form down here, right? Where one part is the residual sum of squares given by least squares, and then this penalty term here. Okay. Notice that I'm saying that these are approximately equal. Oops. That I'm saying these are approximately equal because lambda is not necessarily equal to 1 over s. Okay, so that's kind of a abstraction a little bit. Okay, but it's like 1 over s, and so we'll see that here in a little bit. Okay, so for all of these, we're going to look at parts A through E and look at some feature of the fit of this to the data. Oh, geez, why does it keep doing that? Okay. So whether that's training residual sum of squares, testing residual sum of squares, the variance, the bias, or the irreducible error, and we need to say which of these 1 through 5 is true of A through E. So we'll march through it here. Okay. So the first one we want to know is as we change s, okay, as we increase s from 0 upwards to whatever arbitrary level, what happens to the training residual sum of squares? Okay, so by the training residual sum of squares, we'll talk about it. We can just think about that as kind of the lack of fit or whatever. But let's think about this here. As we take s here from 0 to infinity, say, okay, well, what happens when s equals 0? Well, we're saying that these beta coefficients right here, right, that the sum of their absolute values has to equal 0, okay? And so that is going to be a maximally constrained solution, all right? So, okay, that's fine. But now let's take the opposite. Let's take s equals infinity. Well, s equals infinity. Now the constraint is that the sum of the absolute values of the beta j's just have to sum to less than infinity, but that's no constraint at all. And so when that is the constraint, then what we're left with is, well, the penalty is 0, basically, and we're left with just the residual sum of squares as found by least squares, right? So what is happening as we take s from 0 up to infinity? Okay, well, we're imposing less and less of a penalty, right? Because we had a maximal penalty when s equals 0 and 0 penalty when s equals infinity, right? And so as s gets bigger and bigger and bigger, the residual sum of squares is going to decrease. It's going to steadily decrease. Okay, and so that's our answer here. Okay. All right. So now the next part is, what about for the testing residual sum of squares, right? We just looked at the training residual sum of squares, but what about on testing residual sum of squares, right? On data that the model was not trained on. Okay. So let's just piggyback off of what we were just talking about with the training residual sum of squares. Okay. So one way to conceptualize what's happening here is that as s gets bigger, the model is becoming more flexible, right? Because the penalty is getting smaller and smaller as s gets bigger. All right. So as s gets bigger, the model gets more flexible. Okay, as s gets smaller, it gets more rigid. Okay, and so somewhere in there, so as s gets smaller, we're imposing a larger bias, and as s gets bigger and bigger and bigger, we're accumulating more variance in the solution space, right? And so somewhere in there is going to be, the right is going to be the right answer. Okay, so as s starts at 0, and then it moves, forward, or it moves up, gets bigger and bigger and bigger. At first, we should expect to see the models, or we should expect to see the residual sum of squares decrease, right? Because we're moving away from maximum bias, right? But gradually increase, right? Because at some point we become too flexible and we're adding too much variance to the testing residual sum of squares. Okay, so that's what that should be the answer to 2. The decreases initially and then eventually starts to increase in a U shape. Okay. Now, we're going to come back to the rest of these, but I've adapted an image from the book. I can't remember which figure this is, but certainly you will be able to place it. Now, in the book, so we have the mean squared error here, and it gives the testing residual sum of squares, the variance, and the bias and the irreducible error. And these are going to be the things that we talk about. And going from left to right, you get bigger and bigger values of lambda. But like I said, lambda is kind of equal to, here I'm saying it's proportional to, but even that's not correct. But, they are similar. For every lambda, there is an s whereby we can make, this kind of a, equation. But anyway, but we're talking in terms of s now. Okay, so if this is our testing residual sum of squares, okay, we are, as we move from left to right, as lambda gets bigger, that means that 1 over s is also getting bigger. Okay, but this is where kind of the mental gymnastics comes in. So I don't know how helpful this image is, but if 1 over s gets bigger as we move here to the right, well, that means that s is getting smaller as we move to the right, and bigger as we go over here to the left, right? So we have to read this thing almost from left to right instead. Okay, well, kind of. So, so anyway, when we talk about the residual sum of squares, I'm sorry, the testing residual sum of squares, as s gets bigger, right, moving from right to left, then we should see a drop and then eventually a rebound, a U-shaped rebound. Okay. All right. Now, what about variance? Okay. So we've done training residual sum of squares, test sum of residual sum of squares, and now what about variance? Okay. So as we are already saying, as s gets bigger, there is less and less constraint imposed. So the solution space is getting bigger. There's more room for it to vary, right? So as s gets bigger, there's more and more variance. So as we, so the variance component of the error should steadily increase, okay? And so again, that's what we see here. As s gets bigger, so again, we have to move from right to left in this particular image. Variance should just continue to get larger. Okay. Now, what about bias? Okay, well, this is basically the reverse of variance, right? Because the bias variance trade-off, right? So as s gets smaller, we are imposing larger and larger constraints, right? So now, as I go from big S to little s, in other words, I'm constraining the solution space more and more and more, the bias will increase. Okay. And then finally, for irreducible error, well, again, irreducible error is the error that is not reducible, and so it just remains constant. Okay, so hopefully that helped. I hope that this image was paid off, despite the confusion it might cause by having to go left and right and da-da-da-da-da, but I think if you look at it long enough, it should make sense. So anyway, we'll call that good.